In the 1960s, a Japanese engineer created the term Overall Equipment Effectiveness (OEE) to evaluate how effectively a manufacturing operation is utilized. OEE takes in consideration the cumulative impact of three factors: availability, the percentage of time that a machine is expected to be available for production; performance, the percentage of the actual operational speed compared to the designed or standard speed; quality, the percentage of good product produced compared to all product produced during the machine operating time. In equation, OE is the multiplication of all these three factors. Traditionally, due to the limitation of PLCs, all unexpected events which occur during the manufacturing process will cause the equipment halt its mission no matter what it is doing. To restore the machine, the operator first needs to reinitialize the machine, then the operator can restart the machine. It's obvious that valuable time is lost during the reinitialization process, and this could happen frequently. The author adopts the idea that when non-critical events occur, the machine should hold its position rather than abort its mission. After the operator makes sure that there is nothing critical, the operator can immediately restart the machine. Hence, a lot of time can be saved when a non-critical event happens. ISA 88.01 state machine and pack mail state machine. The core of the current ISA 88.01 state machine is the machine state diagram. The machine state performs conditional logic, which will in turn lead either to further execution within the current machine state or cause a transition to another state. The machine state is the result of previous activities that had taken place in the machine. For example, when the machine is in idle state, it waits for a start command that will cause a transition to running state. When the machine is in running state and receives a pause command, it will go into pausing. Once the pausing procedure has been completed, the machine will remain in the paused state. No parallel states are allowed to be active in one machine at the same time. This pack mail state machine is similar to the ISA 88.01 state machine. Despite its name and origin, pack mail can be applied to any automated equipment. Pack mail state machines and the ISA 88.01 state machine have marginal differences. However, due to the phase manager in Studio 5000 supports the ISA 88.01 state machine equipment phase monitor, which can enable the author to control the machine state in the Compact Guard Logix PLC. The author decided to use the ISA 88.01 state machine for the experiment. To achieve the goal of event classification, Phase Manager can be used to separate events into alarms, reasons, and warnings. Alarm. An alarm causes the system to abort its mission. Reason. A reason brings the system into a hold state. Warning. A warning allows the system to keep running, but it also warns the operator that the performance of the system could be compromised. Phase Manager supports equipment phase command. It can be used to issue commands to the phase manager by ladder logic in the experiment PLC program. To store data at ISA 95 Level 3 database, Factory Talk View SE Alarm and Event Manager should be used. It enables storing events data at ISA95 Level 3 server. Data can be stored in different popular database formats, which can simplify the process for further higher level analysis. However, due to time constraints, this hasn't been implemented by the author. To timestamp events, time synchronization protocol can be used. Traditionally, NTP is the most commonly used protocol which works well on LANs and WANs. However, many NTP clients run on non-real-time operating systems, such as Windows. NTP protocol accuracy cannot be guaranteed. Clock correction of 10 to 15 milliseconds are common. To solve this problem, a novel time synchronization approach called precision time protocol can be utilized, which enables the following features. The event can be timestamped in the POC with sub-millisecond accuracy, enables the factory talk alarm and event manager to capture the event and its duration with high accuracy. However, due to time constraints, this hasn't been implemented by the author either. To prove the hypothesis that by utilizing event classification, automated equipment can increase availability by 20%, an experiment was designed. 4 pneumatic arms of a Rubik's Cube solving machine were used to prove the hypothesis. In the experiment, the pneumatic actuators on 1701 take turns to rotate the cube. Events were programmed to occur during this process. The machine was run in two modes. One was the event classification mode. The other was the conventional mode. An important design requirement of these experiments is that the experiments must be repeatable and reproducible. To achieve this, the machine would be operated in each mode for 50 cycles. Each mode should be operated 2 times by 2 different operators. This would ensure that the experiments are repeatable and reproducible. Repeatability means the variation in measurement taken by a single instrument or person under the same conditions. Reproducibility means whether an experiment can be performed by different people and reproduce the same results. In order to simulate events occurring in the experiment, an event sequencer was created. The event sequencer can generate an alarm to command the machine to abort its mission. It can also generate a reason to command the machine to hold its current position. To achieve this, an array was created to store events information. The index number of the array, called SI for event, is the cycle number in the experiment. 50 cycles of cube manipulation would be run, so the maximum value of the index is 50. For easy configuration, event type 0 will trigger a reason at a preset step. Event type 1 will trigger an alarm at a preset step. For example, for the 4th cycle, when the machine is in the running state and step 610, an alarm will be triggered. A human-machine interface was also created to control the machine. This HMI makes it easy to control an XIC instruction to trigger an output energize or an output latch. It also makes it easy to display a DINT tag value or a bool state on the HMI. While the machine was manipulating the cube, an alarm would cause the machine to abort its mission. four arms and four hands of the machine would retract to its home position. Thus, the Rubik's Cube would fall down randomly. To restore the machine, the operator must manually put the cube into the nest, then reset the machine and restart it. However, due to safety reasons, before the operator can open the door to put the cube into the nest, the operator must turn off the compressed air which supports the pneumatic system. Hence, a lot of time would be wasted. By comparison, in event classification mode, a reason would only put the machine into the held state. The machine would hold its position. To restore the machine from held state, the operator only needs to click the restart button. Thus, a great deal of time could be saved. Based on the results from all four of the experiments, the above graph shows statistical analysis of durations required to restore the machine from either held state or aborted state. The blue histogram shows that it usually takes about 40 seconds for the operator to restore the machine from a critical event which caused the machine to go into a aborted state. The orange histogram indicates that it only takes about 4 seconds for the operator to restore the machine from a held state. To restore the machine from a held state only took 1/10 of the time of restoring it from an aborted state, which means event classification can save a great deal of time for a process which reason often occurs. This graph shows that the available time in the running state can be increased by 12 to 16% with event classification. Although the results disprove the hypothesis that event classification can increase available time by 20%, the increase of available time by 12 to 16% still proves that event classification is an effective tool to improve the performance of an automated machine. The results of the experiment disproved the author's hypothesis. There are three reasons which may account for this. First, the design of the experiment was not perfect. As it is mentioned, due to safety reasons, the author was the only operator, which degraded the repeatability element in the experiment. One key parameter in the experiment was the time duration required to restore the machine from the aborted state. During the experiment, the author became more and more experienced in restoring the machine from an aborted state. Thus, less time was needed to restore the machine. Second, the experiment was only carried out on the 1701 Rubik's Cube solving machine. This also degraded the reproducibility of the experiment. For a different machine, it might take a much longer time to restore it from an aborted state. Hence, a higher percentage of improvement on availability can be measured on those type of machines. Third, for a machine which is working at a factory, a retry logic can be programmed. When a reason causes the machine go into held state, the machine can retry the step which causes the reason. Because an event sequencer is used in the experiment, there is no value for adding such a retry logic in the experiment. However, for a machine in a factory, the automatic retry logic may significantly reduce the recovery duration from the held state. Although the experiment did not prove that event classification can increase availability by 20%, it did prove that event classification can increase availability by 12 to 16%. Fixed line revenue of €2,100 per hour. This would add €250 to €330 extra revenue per hour, which is a considerable improvement. State machine is a key enabler of event classification. Only one major processing activity can be active in one machine at any time, so state machine can help to structure the code tidier. The phase manager is an effective tool to implement state machines. Each equipment state has a separate routine. Each routine will only be scanned when the state is active. This simplifies the programming job for the holding and the restarting logic. Storing events timestamp information in an array in the ladder logic makes it very hard to export the information for further analysis. Because of this, the author manually put all the experiment data into Excel to analyze. This problem can be solved by using FactoryTalk View, Events, and Alarm Manager.